So today we are going to look at stresses and the strain in axial loading condition, and this chapter is continuation of the previous topic that we have seen, that is axial loading and the concept of stresses in axial conditions. So now, if you remember last, pretty well know what is the stress, how it is developed, and how the distribution of stress takes place in a body, and how do we calculate stress. But in this chapter, we are going to look at strain. So strain basically means that elongation of member under the condition of load, and not only deformation is required so that we may assume the structure to perform well within its lifespan, so that we know how much deflection it is going to be under the given stress conditions. And its other function is that sometimes the principle of statics is not able to solve structures which are statically indeterminate. There we apply the concept of strain to determine the stresses and distribution of stress. So strain concept is even more fundamental than the concept of stress, and I would urge you to kindly listen to this topic very carefully, and I will be dividing this topic into smaller segments so that it does not become too large. So let us begin. Now here we see that we have a bar BC and its area is A. So we have seen that earlier we applied the load P here, and we calculated this stress as P by A. This was the thing that we saw last time. But what happens that when you apply the load P, point C is going to move from this point to this point because of the application of load, or you can say that this bar BC is going to deform under axial loading. So this deformation per unit length is called as strain. The deformation per unit length is known as the strain. Now deformation is measured in mm, or it is basically a unit of length, and length is already a unit of length. It is measured in mm or meter, whatever. Strain is a dimensionless unit. It does not have any unit. This is a important thing to remember. Now for a uniform cross-sectional area like this, the deformation is going to be, or the strain is going to be uniform, and you can calculate the strain like this. But suppose we have a member of variable cross-section like this, and it is asked to calculate that what is the strain at the point Q. So you cannot proceed with the steps that we have seen in this case because of the variable cross-sectional area, and the distribution of stress will at the different cross-section will be different. So if you apply P force here, then the stress at these points and these points are going to be different. Therefore what we do is that we take a small patch of delta x length, and then we apply load P here. In the next step, what we see that delta x has elongated by the length delta delta. Now this delta delta is the elongation in the length delta x. So as per our definition, the strain is going to be deformation per unit length. Therefore we write delta delta by delta x. And if you approach delta x to 0, if you take delta x to 0, then you are going to get the strain value at the point Q for the limit of delta x approaching 0. So these are the two concepts of calculating stress. How this is going to be applied in real world, and what is its relationship with the stress, that is we are going to see in further topics. So let us move ahead. Now one thing we need to understand, that there is certain relationship between stress and strain for engineering materials, or for the materials that we are going to use in our applications, or in mechanical world or civil world. Whatever material we use, there is some kind of relationship, or is there any relationship Even for finding that, we need to study these materials under the condition of load. So how do we find whether there is any relationship or not? So the basic concept will be that you can provide strain, calculate stress, or vice versa. You can provide stress to a member, then calculate strain and plot them on a graph. So when you plot, then there will emerge a certain kind of relationship, and from that relationship you can predict the behavior of material as per your applied loading conditions. So whether our material is safe or not, that will depend on what is the relationship between stress and strain for that given material. So for understanding this, we are taking a very simple, let us say that we have a rod, and for measuring the strain we are fixing 2 points. The distance between these 2 points, initial distance between these 2 points is L0, and what we do that we apply tensile force at this end and at this end. We measure the deformation with respect to load P. So two things are measured here, that is load that we have applied, and deformation that is taking place due to the application of load. The deformation is measured by the sensors placed here, or the strain gauge you can say, that is placed here. This application, this type of loading is done in UTM, that is called a UTM machine. In this testing machine you can perform various type of tests on the material that you want to test. So now the stress will be given by load P, applied load, and the area A0 is the original area of cross section, and the strain will be given by change in length delta, that is change in length divided by L0, that is original length. This is your change in length due to application of load. So these parameters sigma and E are engineering stress, that is we are considering only area A0, that is area at the beginning, and we are not taking into account that as the load increases this area is going to decrease. So that these two parameters. Now one thing to take note of is that there are many factors which affect the tensile strength test. First is that what is the temperature of the specimen you are taking, at which the testing is being done. Now what is the speed of loading, and whether the material is ductile or brittle. So what you are going to do is that while keeping other parameters same, you are going to vary this. So you will come to know that how this material behaves under the various ranges of temperature. Now keeping other these two constant, you are going to vary this. So by varying these parameters we will be able to get a picture of stress strain and the relationship for the different materials. Now we are going to look at stress strain graph that we obtain by after doing this test. Now what you see here is that this graph is the representation of stress versus strain diagram. So you have stress on y-axis and strain on x-axis. It is represented by E epsilon, and stress is represented by sigma. So this result is for low carbon steel, that is a ductile material. These both are for ductile material, but even in ductile material we have two categories of ductile material. Now we will see why these two graphs are so different. We are looking this graph for ductile material, and here we notice that in starting portion of very low strain, stress peaks up to a very high value, that is sigma y. It means that in order to get this much of strain you have to apply sigma, then only you are going to have this value of strain. But as you know, as soon as the strain is increased further, you will be having a decrease in the stress value. This decrease shows that the material has yielded. Now the atoms are slipping and material has yielded without any significant increase in stress. We are having a large amount of increase in strain. Now when yielding is complete, this is sigma y is known as yield stress. After yielding is complete, in some materials we see that there is strain hardening. Strain hardening basically means that as you increase the strain beyond yield point, the stress is going to increase. Okay, so here you see that the value of stress has increased from this value to this value. Now the stress will increase up to a maximum point, and this maximum point is called ultimate tensile strength. That means that this material does not has any maximum strength greater than this sigma u value. So we perform strain hardening in some materials to get higher value of sigma y. For example, if we are doing our calculations, then we are going to take this yield value into consideration. But suppose we do the strain hardening of material, and now the yield point has come up to here. So what is going to happen, that next yield point sigma dash will be here, but the ductility is going to decrease. So margin of ductility is going to be this only. So you see that ultimate tensile strength will remain same, but we can work out the strain hardening parameters as per our requirement in different materials. So this is an important point for engineers which they take advantage of. Now if we increase strain further from ultimate tensile strength, then what happens, that the value of sigma stress decreases rapidly. This is rod or the specimen material is going to be necked out, or we say that there is a necking in the specimen. Necking means that there is, you can see the example here, this is called as necking. A neck like region is formed at the point of breakage. So this property or this type of failure occurs in tensile material or in ductile material under tensile loading. So the point where this complete separation takes place is called as value of sigma b, that is the stress at the rupture, and this region to this region is called as necking, this region to this here is called strain hardening, and this is called as yield for the material. Now we need to discuss how this failure takes place. As we have seen that if you do uniaxial loading of a cylinder bar or any member, so the tensile material ductile material are weak in shear stresses. Okay, you need to remember this factor. Ductility is the ability to expand or the ability to stretch out basically under the given loading, but they are poor in shear stress. Okay, so when you apply a tensile loading on ductile material, it is most likely to fail in shear. So under these loading conditions, where is the shear stress maximum, that we have to find, and then only we can predict that how the failure is going to take place. So as we have seen earlier that there is a member, if their section is inclined at 45 degree to the horizontal axis, then the shear stresses generated are the maximum. So this failure takes place at 45 degree angle. This is consistent with our theory. So here you can see example of shear failure. This is not a tensile failure, this is shear failure in tensile loading. Okay, so therefore we need to understand very clearly the concept of principal stresses and how the material is going to fail. We may think that although we are applying tensile loading, it should fail in tension, but it does not fail in tension because it has the ability to stretch out. It fails in shear. Okay, so you need to take into account, and you please visit our previous lecture and see how this 45-degree angle comes, or why the shear stress is maximum there. So these concepts are important as they have very relevant applications in real world. So you need to be sure of the failure mechanism of the system that you are building. Then only we will be able to provide safe and secure machines and environment for the people to live in. Now this is another ductile material, that is aluminum. Okay, so what is difference between these two is that the yield point, this sigma y, is not clearly defined. You see this, there is no yielding, there is simply strain hardening. You can say that strain hardening is going on, and this is your maximum or ultimate tensile strength, and this is your rupture stress. So how do you calculate sigma y? How do you calculate the value of yield strength in such conditions that we are going? In order to calculate yield strength for such materials, we have to follow a method called as offset method. Offset method says that if the yield strength is not clearly defined, then take an offset at 0.2% from the x-axis and draw a line parallel to your initial line, and draw your initial axis, initial slope, and the point where it intersects is your yield strength. So you have to take your 0.2% value here. 0.2% means 0.002 times, and draw a line parallel to this line, and I think it should intersect here, and this value will be your yield strength value. So this is how the yield strength is calculated in such materials. That is, you have to use offset method. Now after seeing tensile strength, let us come to the stress strain diagram for brittle materials. So brittle materials means that they are very poor in tension, and very effective in compression. The brittle material shows very simple stress strain curve, that as the value of strain increases, the value of stress also increases, and there is no such yielding. The only point of to be noted is the point of rupture, or where the this material breaks, specimen breaks. That is called as ultimate strength or the breaking stress, whatever name you would like to say. So there is no yielding, no strain hardening, nothing, only rupture. Surface is like this. This is your tensile failure, and tensile failure is at 90° to the application of load. So the orientation of surface is matching with our application of force, or the consideration of force. So here we also have the confirmation of our theory with the test that we have performed. There is no necking, nothing, because the brittle materials are poor tension. Now true stress strain, as I have told you in the first slide, that when we are calculating stress value, we are taking P by A naught, engineering stress, and when we are calculating strain values, we are taking delta by L naught, that is original length. But these are not representatives of true stress and strain, because area keeps on decreasing and length keeps on increasing. So true stress to be plotted will be equal to load applied by actual area of the specimen that is at that load, and true strain is going to be the summation of change in length divided by actual length. L is the actual length at that point. So you have to integrate this, and the value you get, that is natural log of L by L naught. So this is your engineering strain. Now you have to understand this graph, that in the initial portions of the strain, or where for the values of low strain, the graph is almost kind of same to the engineering stress versus strain graph. But the remarkable difference happens here, that while in engineering stress versus strain we had the ultimate strength and this breaking was here. Okay, but you are seeing that the rupture takes place and there is no necking as per this graph. This happens because this area, this keeps on decreasing, so the stress always keeps on increasing, it never decreases. So this curve, this never exists. This depends on our choice, that whether we want to stress strain for our project or engineering stress. And normally for low values of stress strain we are comfortable with engineering stress and strain, but you need to be familiar with both the aspect of our testing method and the graph that we get. So this is for now, and in the coming lecture series we are going to dive deep into this topic. We will see Hooke's law and its application, and further more topics shall follow. So please subscribe and please like and share so that this channel can grow. Thank you very much.